Okay, so now let's go back to comparing two groups again, independent samples. Well, independent samples, sometimes we come across them and we have equal variances. Sometimes we come across them and we have unequal variances. Well, let me see. I got a couple of formulas here I need to show you. Let me see if I can't get to them. No, we're not going to be in there. Let me open up an Excel file. Okay, see if I got another window open here. Nope. Open. Okay, let's see. Let's open this one. In this problem, we're comparing two. We did something. We did this in a lab also. I don't know how far we got with it, but I'm comparing two groups. Sample size for each group is 5, right? Could be different sample size. Don't have to be the same sample size. In fact, most of the time, because of dropouts, errors, or whatever, you wind up dropping some data, and they're rarely exactly the same size in real life. But we're comparing the calorie count in from two recipes as they're prepared by as a restaurant, because they're not always the same. There's some variability in how they make it, a particular restaurant, so on and so forth. We're comparing whether or not they're the same, or the mean calorie count is the same or different in these two groups. So we're going to calculate a mean for this group. And we're going to calculate a mean for this group. Okay, so the means are just a little bit different. They're not a whole lot different, these two means are there. That's a very small sample size too. So I'm a little bit worried about whether or not we're going to be able to prove that if there's a difference. Well, now we don't have no one's told us what the standard deviation is going to be for every time this is prepared in these restaurants. Maybe they make, there's 20 restaurants and they make 100 of these in each restaurant every night. We're not going to be sampling every one of these. So we don't have a population standard deviation for either one of these. So we have to calculate our standard deviation based on what we know about the variability within these two samples. Well, there's two things that could be happening here. It could be that even though the means are different in these two groups, that the variability is the same in the two groups because of things that lead to them being variable. Maybe measuring how much flour you put in, how careful you are about mixing, and so on and so forth. Maybe that's the same whether you do it one way or do it the other way. So I'm going to say to myself, well, gee, I'm going to assume that the variances in these two groups are equal to one another. Okay, that's a big jump, but I'm going to make that assumption. Okay, so here's our means right here. Well, when I'm in that situation, let me pull up a formula here. Make sure I got the right one. When I'm in that situation, whoops, got the wrong one. Didn't want to do that. Let's see if I can't find this formula here. Where did I put it now? Where did I put that now? I didn't put it in here, I guess. I didn't copy it in here. Okay, I'm gonna fly without a net here. Okay, so now you guys may remember that if you assume equal variances, right? Well, that's a little bit of a leap, that assuming equal variances, isn't it? If you assume equal variances, we use a particular form. I want to find this thing. I really want to make sure I get this right. Tell you what, I'm gonna do the SPSS version of this, right? Because I think it's unlikely that you'll have the time on the exam to calculate this using the raw formulas. Okay, but I'm going to do the SPSS version of these to start off with. Let's say that we have two situations that we can have. We can have independent samples, two samples that we take like these cakes, and they can have equal variances, or we can have another situation where we take two samples and they have unequal variances. I'm going to look at those both. I'm going to use SPSS to start out with, and we have a limited amount of time here too. We're already an hour in. Okay, so I'm going to start out with SPSS. I'm going to reopen SPSS and look at some more data that we have. Okay, so now let's take a look at this situation one, where we have independent samples and we have equal variances, or we think we have equal variances. Well, here's our data here. We have in this variable is a calorie count for two different recipes that are served in dozens of restaurants and hundreds of times a day. And we want to know whether the average calorie count is the same for both of them. And here is which of the two recipes it is. Number one is recipe number one, recipe number two is recipe number two. Okay, so I need this factor. This represents that my first sample, right, is recipe number one. That's the number of calories, recipe number one, number of calories for my second sample, my third sample, and so on and so forth. I want to compare the mean calorie count for recipe number one to the mean calorie count for recipe number two. I'm looking at the numbers and the variability looks pretty similar. So I think that the variance of these two groups is going to be similar. Okay, so I'm going to go ahead and go up here to analyze. I'm going to go to compare means. Oops. Let me get back here. Go to analyze, compare means, independent samples t-test. These are two independent samples, right? We went out and took one sample. It's not the same restaurant twice. It's not the same cook twice. We went out and got different samples. Independent samples. Okay? And I'm going to say to myself, well, gee, what I'm comparing here is I'm comparing the calorie count, the average calorie count, but I want to compare recipe one versus recipe two. Notice now it has a couple of question marks in here. It wants to know, how did you define recipe one and two? Well, I know I defined it as one, number one, and number two. If those are blank, you'd have to fill those in. Okay, so I'm going to compare those two groups, recipe one group versus recipe two group, to one another. I'm going to click OK. So my null hypothesis is that the average calorie count is the same. My alternative hypothesis is that the average calorie counts are different. So I'm going to go to my output window, and let's see what I got here. Okay, so here are my averages here. Okay, my average calorie count, as it was in Excel, came out to be 2867 for one. For group two, it came out to be 2895. Well, SPSS calculates the standard deviation for each one of these. It's a little bit different, right? The standard error for each one of these things, okay, based on the sample size, right? That's going to be that divided by the square root of 5 and so on for each group. SPSS then does an analysis to determine whether the standard deviations, we can say that the standard deviations, the variability between these two groups is the same or different. Well, this is our output here in independent samples t-test. Okay, and we get two lines. SPSS actually does this calculation twice. On the top line, it does the calculation with equal variances assumed. Okay, well, you guys remember in the formulas, I'll post this later on along with these tables. You guys remember in the formulas that you used one version of your formula to calculate your t-score or your z-score when the variances were equal, and you decided how you were going to combine the variances, right? In other words, for equal variances assumed, you calculated a pooled variance, then you multiplied that by the differences in, by the 1 over the sample size, square root of 1 over the sample size for each one of the groups. Okay, because sample size had a impact on it, right? So the calculation of the standard error was a little bit more complicated than it was before because you have the advantages of pooling the two variances into a single group. Okay, now you use a different formula, but then when you did that, the calculation for degrees of freedom was quite complicated. I don't have those available right now, and I don't want to kill too much time trying to write them out and so on, since we have a limited amount of time left. Because it's very difficult to get a lot of this stuff. You know, I'm limited to like 10 minutes or 15 minutes per video on YouTube, and that's what I've been using lately. So I don't want to make this go too long, and I know I want to keep it relevant. Okay, so at any rate, so this is equal variances assumed, this is equal variances not assumed. Okay, so now this part, this box right here, this box of 4 entries right here, Levine's test for equality of variances, is where SPSS decides whether you should use equal variances assumed or equal variances not assumed. It calculates both, but it gives you this information in order to help you decide which to use. Okay, so now based on what you know about how we do things in SPSS, how we put together, or excuse me, in statistics, how we deal with hypotheses. Would you say that I'm going to start with the assumption my null hypothesis is going to be that the variances are equal or that the variances are different? What do you think? Take a guess. Equal. Okay, I like that. Equal sounds good to me, right? Because that's usually the kind of thing that we do. So we're going to start out with the assumption that the variances are equal. So that means that we're only going to use this top line in our output for SPSS unless we have a reason to reject the idea they're equal and use the bottom line. Well, this test for the equality of variances is what SPSS does to tell you the likelihood that they're not equal. What's the probability that that you would be wrong if you reject line 1 and say that they're not equal? Well, let's see. Just as before, it calculates a statistic and it calculates a significance, a probability. This again is your probability of being wrong if you reject the null hypothesis, which is equal variances assumed. So your probability of being wrong if you reject the null hypothesis is 17.5% chance of being wrong. What do you think we should set as our limit for rejecting the null hypothesis? What's your opinion on that? Give me an opinion. What level should we set that to? Okay, what alpha error are we willing to accept? 5%. I agree. We want to set that to 5%. Since this is larger than, we have a bigger chance of being wrong if we reject the null hypothesis than 5%. We fail to reject the null hypothesis. We just stay with the assumption that the variances are equal. So in this case, we're going to use the top line. Had this significance been less than 0.05, we would have said, that's a justification to reject the null hypothesis and use the alternative hypothesis. Okay, so we're going to stick with the top line in this particular case. And the top line tells us that the difference between these two means, the t-score for the difference between these two means, is negative 0.237. Very small number, right? So we know already that we're not going to be able to prove that these two in this tiny little sample are different from one another. Not that big a surprise. Degrees of freedom was 8 because we know in this particular situation where we're dealing with pooled samples, it's just sample size 1 plus sample size 2, right? Minus 1 for sample 1, 1 for sample 2. So it's 10 minus 2. Degrees of freedom is 8. When you do equal variances not assumed, it's a relatively complicated formula that you have to complete in order to determine the degrees of freedom. So it comes out to be kind of an odd number there, very strange number. A lot of times what we wind up doing is that we say, well, forget about the fact there's two samples and use the sample size for the smaller group for your sample size for calculating your degrees of freedom. Okay, so a lot of times if you do this manually, you won't bother to calculate degrees of freedom. If we get a chance, I'll lay out all those formulas and stuff like that, another time, and we'll look at them carefully, and that'll make some more sense to you. But so we're just sticking with the top here for now. So if I go across here, my significance, my probability of being wrong, if I say there's a difference between the average calorie count for these two groups is 81% chance of being wrong, can I reject the null hypothesis that they're the same, that the calorie counts are the same? Do I reject? Opinions, please. Reject or not reject? Come on. I'm going to wait until somebody gives me some feedback. Okay. We got to reject. Thank you, Sarah. Like pulling teeth, right? Okay. Everybody agree with that? Does everybody agree with that? That we would fail? Excuse me. I just misspoke because I expected you to get it right. We failed to reject the null hypothesis. Null hypothesis is that the two means are the same, right? And we failed to reject because we have 81.8% chance of being wrong if we reject the null hypothesis. So we fail to reject the null hypothesis because the significance, the p-value for our t-test has to be less than 0.05 for us to reject the null hypothesis. Okay,